Hello, welcome to another short video on electronics by Q in Motion. Today we're going to talk about some cool tricks with relays. Here I have the same relay from the previous video with the coil connected to positive and negative. Remember, you can hear the coil clicking there, okay, every time it connects. Now, what happens if instead of connecting the negative straight to the negative side of the supply, I connect it to one of the terminals of the contact and I connect the normally closed contact to negative, okay? Well, apparently we got ourselves a buzzer, if you can hear it, right? So how does this work? Let me stop it and explain for a minute. Basically, this is the black here and the yellow are the normally closed contact. When I connect these to negative, because the contact is closed, the electromagnet in the relay is energized and it starts to pull the contacts apart, right? Now, as soon as the contact opens, the coil loses energy and the contacts are released again. Once they make contact, the coil is energized again and the cycle repeats. And that's how we got a buzzer. Now, it is actually not advisable to use this as a buzzer because you're opening and closing that contact many times per second with an inductive load, and that will produce the contact to wear quite quickly. So this is actually more of a curiosity than actually a practical use for it. Now let's do the same, but let's connect an oscilloscope to the coil of the relay and see what kind of voltages we are getting here, right? So I'm connecting the oscilloscope probe between the negative side of the coil and the negative side of the supply. And I'm going to be connecting this here and I'm going to be looking at the oscilloscope and see what is it that I'm getting. Okay, so what you see on screen is a photo from the oscilloscope, and as you can see, the vertical scale is at 100 volts per division. And we have some spikes there that are over 2 divisions in height. So that means those spikes are over 200 volts, okay? They're very short and the energy there is not very high, but the voltage is 200 volts or more. It's actually closer to 250. So if you haven't watched our video on current sources and our video on inductors, I would advise you to look at it to understand why that is happening. But the short answer is every time you disconnect abruptly an inductive load, you will get some huge voltage spikes. Okay, so what I'm going to do now is to try to take advantage of those high voltage spikes and harvest those in order to generate a higher voltage. So what I have here is a diode connected from the coil of the relay to a capacitor. This big block here is a capacitor, 1 microfarad capacitor rated for 275 volts. Okay, so I'm going to connect the buzzer again and let's see what happens. The meter is measuring the voltage on the capacitor. As you can see, the voltage starts rising and it will reach a maximum of about 95 volts. So on every spike is putting the diode in forward conduction mode, right? So a little bit of energy gets transferred from the spikes into the capacitor, and that repeats over and over several cycles, and the capacitor charges to pretty much the peak voltage of those spikes. Okay, so that's the basic principle of a boost converter in a switching regulator. So that allows you to generate a voltage which is higher than the supply. Now, Unless you are actually trying to build a boost converter, those high voltage spikes are not something that you want. So let's see how we can mitigate those. The way of mitigating those is with a diode. So we put a diode in parallel with the coil of the relay, just like this. Okay, so what the diode does is provides a path for the current and the energy in the magnetic field in the inductor inside the coil of the relay to discharge. Okay, so if you want to have a look at the long video on relays, that's explained in detail. So let's see how this looks on the oscilloscope screen now. Let's connect this back. And let's have a look at the oscilloscope screen. So this is what the screen of the oscilloscope looks like. We got rid of those spikes. If you pay attention on the lower left corner, it's the scale is 2 volts per division, right? So those square waves are about 3 divisions or 6 volts. So why is that? The power supply is 5 volts and the diode, what it's doing is limiting the voltage of the spike to the supply, which is 5 volts plus whatever it is on the diode. So it's going to be like 5.7 volts. In the oscilloscope you cannot see that much detail, and it's probably a bit higher, maybe 5.8, so it looks like 6 on this scale on the oscilloscope. Okay, now we have our buzzer again, and let's take this capacitor. It's fairly big, it's 1000 microfarads, and we're going to put it in parallel with the coil of the relay, and let's see what happens. Do you hear it? Okay, let's connect something to the contacts to see actually what's going on with those contacts. Okay, so now I connected an LED to the normally open contact, and we see that the LED is flashing. So we got ourselves a flasher with nothing else than a relay and a capacitor. So how does this work? Well, this is the same buzzer that we had originally, only when the coil fires, it also charges the capacitor, right? And the capacitor will hold the charge and will hold the coil activated for a little while, right? It's less than a second, of course, as you can see and hear on the video, but it is enough to control the frequency of this flasher. The bigger the capacitor, the slower the flashing is going to be. Okay, that is all for today. I hope you learned about some cool tricks with relays, and we'll see you next time. Thank you. Bye bye.